Welcome to the Chemistry 209 Masterclass series. This series of lectures is intended to highlight the key concepts of introductory spectroscopy and structure. This lecture, Masterclass 2, discusses how we formulate quantum theory and how this formulation may be interpreted in terms of quantized energy levels and atomic and molecular orbitals. There are two equivalent formulations of quantum mechanics. The first, matrix mechanics, was developed by Werner Heisenberg, and it is a mathematical approach that deals with transcendental algebra. The matrix mechanics approach is ideal for computational quantum chemistry, but it isn't particularly accessible to beginners. Instead, we will focus on the second formulation of quantum mechanics, known as wave mechanics, which was developed by Erwin Schrödinger. Schrödinger's formulation uses classical wave theory to describe the wave-like natures of particles with a wave function. Discrete quantum states arise when matter waves constructively interfere to produce a standing wave pattern. In this way, particles can only exist in certain quantized states. We will discuss how this can occur in 1, 2, and 3 dimensions with the illustrative examples of a particle in a one-dimensional box, a particle on a ring, and spherical systems. As you will see, these three basic models can be used to describe vibrational and rotational motions of molecules and electronic orbitals and atoms. The rules of wave mechanics are simple. For every molecular system there exists a wave function, psi, which contains all of the information we can possibly know about the system. The wave function is the solution to Schrödinger's differential equation for the system, and it depends on all spatial coordinates of all the particles. The wave function must be single-valued and continuous, and the probability of finding a system with a particular configuration is proportional to the square of the wave function. We can also introduce a normalization condition, whereby the square of the wave function when integrated over all coordinates must equal 1. Simply put, this means that every particle must exist. With these rules in mind, let's do a thought experiment. Consider a quantum particle that is trapped inside a one-dimensional box. Our particle is confined by infinite potential energy barriers to move along a line of length L. Within the box, our particle experiences zero potential energy. We know that the total energy of the particle is equal to the sum of its kinetic energy and its potential energy. The potential energy we've already said is zero. The quantum mechanical operator for kinetic energy is minus h bar squared over 2m times d squared by dx squared, which you can compare with the classical kinetic energy of p squared over 2m. Thus we find that taking the second derivative of the particle's wave function must return the wave function, but multiplied by some constant. For possible wave functions, we need look no further than sine kx or cos kx. Both of these functions are continuous and single-valued, and both satisfy the Schrödinger equation, since the second derivative of either returns minus k squared multiplied by the original function. In fact, we could propose a general solution that employs both the sine and cosine functions. So how does this lead to the idea of quantization? Since our particle is confined to the region between 0 and L, its probability of existing outside this region is 0. Thus, for x less than 0 or x greater than L, the wave function must be 0 owing to wave mechanics rule number 4. We've also stipulated that the wave function must be continuous. Therefore, the wave function must also be 0 at x equals L or x equals 0, owing to wave mechanics rule number 3. If we take our limit of x equals 0 and substitute this into our wave function, we find that for the wave function to be 0 at x equals 0, the constant multiplicand of our cosine function should also be 0. Thus, our wave function becomes a sine kx. By substituting our other limit, x equals L, to yield a sine kl equals 0, we then find the trivial solution of a equals 0, i.e. there is no particle, or kl equals n pi, where n is any positive integer. Recalling that k equals the square root of 2me divided by h bar, this simple derivation shows us that our confined particle has energies that depend on particle mass, the box length, and quantum number n. Normalizing our wave function ensures that the square of the wave function equals 1. A plot of the particle in a box energies for our given box length shows a ladder of energy levels with an increasing separation between each rung owing to the n-squared quantum number dependence. Also overlaid on the energy level plots are the wave functions corresponding to each energy level. Thus we see that each higher energy wave function is just a higher harmonic of the lowest energy or ground state wave function. Owing to its shape, the particle in a box potential energy well is also known as a square well. The square well model, although very simple, teaches us some very important things about quantum theory. First, we see that energies are discrete rather than continuous. We also see that, like standing wave patterns, the nth wave function has n extrema and n-1 internal nodes, or points where the wave function goes to 0. Furthermore, we find that as L and M increase, level energies decrease, so as particle mass and/or size approaches the bulk scale, quantum structure collapses into essentially an energy continuum. This, of course, is reminiscent of Niels Bohr's correspondence principle. Finally, note that the n equals 1 state is our lowest energy level, but it is not at an energy of 0, which we might expect classically. This is a quantum effect that is known as zero-point energy, and it arises due to the Heisenberg uncertainty principle, which in one assertion states that the product of uncertainties in the position and momentum of a particle must be greater than or equal to 1/2 of Planck's reduced constant. Recalling that a particle's position and momentum determine its potential and kinetic energies, we see how this uncertainty must result in a ground state that exists above the classical potential energy minimum. The lessons that we learned from square wells carry over to our description of electronic motion in atoms and molecules, and to rotational and vibrational motions in molecular systems. In the case of orbital and rotational motion, however, our changing dimension is angle. Similarly, radial and vibrational motions are concerned with changing radii. Imagine that we take the two ends of our one-dimensional particle in a box axis, wrap them around into a circle, and join the ends to form a ring. Now, rather than describing the particle's position along an axis, we instead describe its position in terms of an angle around the ring. We find that our particle's standing wave patterns, or steady states, must join in a head-to-tail fashion, and that the nth wave function has 2n extrema and 2n nodes. Whereas the particle in a box energies were inversely proportional to ml squared, the particle on a ring energies are proportional to mr squared, where r is the ring radius. Note that mr squared is the particle's moment of inertia, which can be thought of as an angular analog to mass. We will discuss this idea in much more detail in our section on rotational spectroscopy. Note also that the rotational energy level ladder is described in terms of a rotational quantum number, L. Here, however, a value of L equals 0 is allowed in contrast with our solution to the particle in a box. In other words, there is no zero-point energy for rotation. For the particle in a box problem, the wave function had to join continuously to the zero probability region outside the box. Thus, n equals 0 would imply that there was zero probability inside the box as well. In the case of a particle on a ring, or rotational wave function, continuity is satisfied as long as the wave function joins smoothly to itself whenever the angle phi is increased by 2 pi. This is possible for L equals 0 if the wave function takes a constant value equal to the square root of 1 over 2 pi. The Schrödinger equation for the hydrogen atom resembles a three-dimensional version of the particle in a box Schrödinger equation. Since atoms are spherically symmetric, the Cartesian coordinate system is often replaced with spherical polar coordinates to make the math a little easier to deal with. We also describe the atom in terms of a single reduced mass for the electron-proton system, which is equal to the product of the electron and proton masses divided by their sum. The total wave function for the hydrogen atom can be thought of as a product of a radial function, which depends on the electron's distance from the nucleus, and the spherical harmonic, which depends only on the electron's polar and azimuthal angles. The form that these functions take depends on three quantum numbers: the principal quantum number n, the orbital angular momentum quantum number L, and the orbital angular momentum projection quantum number m sub L. M sub L is also sometimes referred to as the magnetic quantum number because the circulating charge described by M sub L produces a magnetic field in the same way electromagnets are produced by passing a current through a coil of wire. The radial part of the wave function is essentially a solution to the one-dimensional particle-in-a-box problem. In this case, though, the box has length r, the particle has mass mu, the reduced mass, and the confining potential is a Coulomb potential which defines the electrostatic attraction. For the radial wave function defined by the quantum numbers n equals 1 and L equals 0, we see that the wave function value, and therefore the probability of finding the electron, is highest at the nucleus. This probability distribution, which is that of the 1s atomic orbital, decays quickly with distance away from the positive charge. For the 2s orbital, there is also a relatively high electron density at the nucleus. This is a characteristic of s orbitals. For the 2s radial wave function, however, we find a radial node. Radial nodes are radii at which the radial wave function has a value of 0. Similarly, the 3s atomic orbital has two radial nodes. The number of radial nodes for an atomic orbital is equal to n minus L minus 1. It is important to remember that these radial nodes actually represent nodal surfaces in 3 dimensions. Notice that the radial wave function changes sign at the radial nodes. On one side of the node, the radial wave function is positive, on the other it is negative. As we will see in our section on molecular orbital theory, the algebraic sign of the wave function has important bearing on how orbitals overlap. Also, remember that a negative value for the wave function does not imply a negative probability, since it is the square of the wave function that gives the probability density. A plot of the orbital energies for the hydrogen atom is shown on the left. Here we see that there are an infinite number of quantum states that converge to the ionization limit. Note that the orbital energies are, to a first approximation, dependent only on the principal quantum number, and that the energy expression is the same as the one derived by Niels Bohr. We can also define a mean atomic radius, which is an averaged value owing to the uncertainty in the electron's position. The spherical harmonic part of the total wave function defines the angular distribution of the electron density. The quantum numbers that we use to describe the spherical harmonics, L and m sub L, define the magnitude of the orbital angular momentum and its orientation in space. The familiar shapes of atomic orbitals arise due to the angular distributions defined by the spherical harmonics. The L equals 0, m sub L equals 0 spherical harmonic yields a spherical s orbital, while the L equals 1, m sub L equals 0 plus minus 1 set generate the 3 orthogonal p orbitals. Here we see that the number of angular nodes in our wave function is equal to the L quantum number. For the y10 harmonic, there is a nodal surface at theta equals 90 degrees, while the y11 harmonic exhibits a nodal surface at theta equals 0 degrees. As was the case with the radial wave functions, the nodal surfaces introduced by the spherical harmonics are also associated with a sign change of the wave function. Thus, the two lobes of a p orbital have opposite sign. This difference in sign is also sometimes referred to as a difference in phase. By building up our picture of the hydrogen atom from our one-dimensional model, we can now see how quantization arises in atomic systems. It is also now clear how and why nodal surfaces arise for atomic orbitals. Furthermore, we see that the energies of the hydrogen atom quantum states increase with the number of nodal surfaces, and that to a first approximation, level energies depend only on the total number of nodes, which are defined by the principal quantum number n and the orbital angular momentum quantum number L. When we extend our theory to multi-electron atoms, we find that orbital shapes are very similar to those of the hydrogen atom, but that orbital energies are very different. A major factor for causing these energy differences is the z squared term in the energy level formula. Most atoms have more than one proton in their nucleus, which means that there can be stronger interactions between the electrons and the nuclei for these species. A second important factor is the fact that in multi-electron systems, the electrons interact with one another. We can think about this classically in terms of the electrons repelling one another. You will see in Masterclass 4 that there are also quantum mechanical interactions known as electron correlation and exchange that can also influence level energies. Finally, owing to the electron probability density distributions, we find that electrons can potentially be located at a range of distances from the nucleus. Thus, electrons that spend more time relatively close to the nucleus owing to their probability density distributions experience a greater effective nuclear charge than those electrons that spend more time relatively far from the nucleus. This phenomenon is known as electron penetration or shielding, and it is often treated algebraically by introducing a quantum defect term into the energy level expression. We will talk more about this in Masterclass 3. We can see the effects of nuclear charge and electron interactions in this plot of atomic orbital energies. The helium cation 1s atomic orbital is 4 times lower than the hydrogen 1s energy, owing to the z² factor in the energy level expression. However, if a second electron is added to the helium 1s orbital, the level energy rises due to interactions between the two electrons. For the 2s and 2p orbital energies, we see a trend of decreasing energy with increasing atomic number. This trend is again due to the increasing nuclear charge. The rate of decrease for the 2s orbital is, however, larger than the rate of decrease for the 2p orbital energies. Recalling the form of the radial distribution functions for the 2s and 2p orbitals, we now see that the 2s orbital has a higher degree of penetration to the nucleus and thus experiences a higher effective nuclear charge than the 2p orbital. As a result, the 2s orbital energy is increasingly stabilized with respect to the 2p orbital as nuclear charge increases. We will see in Masterclass 5 that this energy separation between the 2s and 2p orbitals has important consequences with regard to molecular orbital energies. Despite the differences between many electron systems and hydrogenic atoms, understanding hydrogenic systems is still useful. Like one-electron systems, multi-electron atoms also have ladders of energy levels, with an infinite number of rungs converging to the ionization limit. Multi-electron systems also have wave functions that oscillate increasingly rapidly in space and have more nodal surfaces as energy increases. Furthermore, like the hydrogen atom, the total electronic energies of multi-electron systems are the sum of the energies of all the electrons. However, unlike hydrogenic atoms, multi-electron systems have no explicit expression for orbital energies. We cannot solve the Schrödinger equation for these species exactly. We can now use our understanding of many electron atoms to start building up a basic understanding of molecules, since molecules are also many electron systems, but with 2 or more positively charged nuclei. Like atoms, molecules have an infinite number of electronic states that converge to the ionization limit. However, for molecules, the energies of these electronic states vary with nuclear configuration. For diatomic molecules, we can prepare a 2-dimensional plot of electronic potential energy versus bond length. In this way, we see that the electronic states of diatomic molecules are better thought of in terms of potential energy curves. For polyatomic molecules that have 3 or more atoms, electronic states are described by hypergeometric potential energy surfaces. The description of molecules is more complicated than that of atoms because electronic and relative nuclear motion must be accounted for. The Born-Oppenheimer, or clamped nucleus approximation, simplifies this problem. Owing to the fact that nuclei are thousands of times heavier than electrons, we can assume that nuclei are stationary on the electronic timescale. This assumption allows us to treat electronic and nuclear motion separately, which means that the electronic Schrödinger equation can be approximated as depending only parametrically on nuclear configuration. Notice that the total energy of the molecule then becomes the sum of the nuclear and electronic energies, but that the total wave function is the product of the electronic and nuclear wave functions. It is easy to see why the total wave function must be a product of the electronic and nuclear wave functions if we remember that these functions describe probability waves and that probabilities multiply. We can then extend the Born-Oppenheimer approximation to the relative nuclear motions themselves, since we know that molecular vibrations occur on a timescale that is much faster than rotation, which is again much faster than the time required to flip a nuclear spin. As a result, we can represent the total energy of the molecule as the sum of its vibrational, rotational, nuclear spin, and electronic energies. This allows us to treat each distinct type of molecular motion individually so as to gain a complete understanding of the molecule in question. This will be our approach for Chemistry 209. Before we begin our studies of molecular systems, though, we will need to explore the structure of atoms in more detail in Masterclasses 3 and 4. See you next time.